Anyway, so today I'm mostly going to be talking about the chiral anomaly from the Dirac-Lagrangian, and then understanding how this corresponds to non-invertible symmetries in the general framework of our charge operators that we construct from nova currents and so forth. Okay, so today's one is about anomalies, chiral anomalies, and non-invertible symmetries. Okay. So there's really like two parts to this. The first, I'm mostly going to be talking about part one, which will be the chiral anomalies. And then given enough, if I have enough time, we can then talk about the non-invertible symmetries aspect of interpretation of them. Um, a lot of that relies though on the understanding of topological field theories, which I'm not particularly well versed in, but I can go through, there's a nice paper, the original one, in particular by what is their name? What is the, let me put up the archive code. So for non-invertible symmetries, or the non-invertible symmetry interpretation of the chiral anomaly is by Choi, Lam, and um, Heng Xiao. And the archive code is, let me write this down. It's going to be 2205.05086. There's also one by, let me confirm the authors. It is Cordova and what's her name? Give me a second. Um, yeah, let me just remind myself the other people's names. So there's one other author. I can't remember them off the top of my head. But when it comes, oh, Choi and Cordova, is it? Oh, but anyway, that's another reference which I will copy over later when we get to it. And that'll be, but it's not relevant for the meantime. Okay, so the main idea for anomaly is that you start with some sort of classical theory and you have symmetries, but then underneath a quantization procedure, they're not going to be preserved. So basically the symmetry gets broken. But not in the sense of a spontaneous symmetry breaking sense, but just in the sense of like they no longer are symmetries on the action. In the case of gauge symmetries, this is not allowed because then, we want the gauge symmetries to still be gauge symmetries. But for global symmetries, it's okay. And that's basically the context behind the chiral anomaly is that it corresponds to a global symmetry of the Dirac-Lagrangian, which does not survive for the quantum theory. Okay, so just as a reminder about the Dirac-Lagrangian, so we start with the action. So we've got our Dirac spinor fields, psi, and say psi bar. And then we have our action, which is just going to be Lagrangian over d spacetime dimensions of the Lagrangian. And just for a bit of simplicity, I'm just going to write dv just to have the volume element. And the Lagrangian is given by psi bar I d slash psi. And then if it has a mass, then it's going to be given by m psi bar psi. But in the context of what we'll be looking at, in order for have the axial symmetry, we want it to have just a zero mass. So then we're just going to consider the zero mass case. Okay, so just a reminder, this d slash is known as the Dirac operator, and it's given by the contraction with the gamma matrices and the gauge covariant derivative, which in this case is d mu minus I g a mu. And in general, you can also have like a spin connection term. But for our sakes, we were just going to consider a flat manifold in which we define our theory. So we'll just kind of we'll just ignore this term. Okay, so the gamma matrices really depend on the signature in which you're working in. So for example, in the gamma matrices for say four spacetimes, Minkowski spacetime, you've got the metric if you got like the plus minus signature, then you want it such that these one squares give you I, and then the minus components will give you minus the identity, and these matrices are going to act on the spinor fields and so forth. Okay, so let me just write that. These ones map a Dirac spinor into another Dirac spinor. Okay, so another important element which we would like is relevant for defining the chiral symmetry is going to be the chiral element, which in our case for D equals 4 Minkowski is going to be, I'm going to write it as gamma 5, but in general, for this talk, I'm going to be considering just D space-time dimensions. But when I write gamma 5 lower script, I just mean the chiral element. Sometimes people write gamma star as well, but just for consistency, I'm going to write gamma 5. Okay, so in this case, it's going to be um, I, gamma 0, gamma 1, gamma 2, gamma 3. And so this is going to satisfy gamma 5 squared equals I. Oh, and I also forgot to mention these ones also satisfy for the gamma zeros. These satisfy if you take the Hermitian conjugate, they're going to give gamma 0. Let's just write it like this. If mu is 0, and then gamma minus gamma I if mu is I. And then these ones are going to be self-adjoint. So then gamma star, a dagger, is going to be gamma 5. Okay, so we can continue with this. Oh, also in the Minkowski's signature, the Dirac spinor is written by the Hermitian conjugate with gamma 0 attached. Okay. We will also then go change signature into Euclidean. I'm still not quite on top of how to transform from the Minkowski signature into the Euclidean signature, but just to the general idea is that a lot of these properties will still hold over, but for the meantime, let's just consider in the Lorentzian signature, and then we can try and understand how these transform into the Minkowski, into the Euclidean one. Okay, so with the Dirac-Lagrangian, we have two different global symmetries immediately obvious. Let me just rewrite this down. So it's going to be Dirac massless. It's going to be psi bar I dagger D slash this one. And then so we have what we call a vector U1 transformation, which will be just multiplied by a phase e to the I alpha psi. And then this is going to be conserved. And then so, for example, this one is going to go to psi e to the minus. And then we have what we call an axial symmetry. So this is going to be like, say, the chiral symmetry, which is going to be, this one gets mapped to e to the I alpha gamma 5 psi. Oh, and also alpha is meant to be a real parameter, which, yeah, okay. So then we have this one is going to psi bar is going to go to psi bar e to the I alpha gamma 5. Okay, so the important property about this is that both the conjugate one and also the unconjugate, just a regular Dirac spinner, are both going to have the plus I alpha gamma 5.
Jonathan, I'm just gonna stop you right. I'm a bit confused about your U1 symmetry, the first one.
Mhm.
You want psi bar transform into psi
Oh,
e to the
sorry, I
power
forgot
minus.
to write the. Ah, thanks for that.
Okay, okay.
That was just
Mm.
a notation error. Yeah. So these ones are meant to be transforming like this. So if you check the formal details, you'll see that these are indeed the proper symmetry. So the important point is that in the Euclidean signature, these ones are meant to also hold. Um, though from what I've seen in Euclidean signature, they define the psi bar as just psi dagger. But then this doesn't quite make sense to me, say how you would show the right hand transformation for, let me find this one here, this one, how this one would transform in such a way. But it's supposed to hold. But I guess that's some formal technical details which need to be checked. Okay, so now we can proceed on to so what I want to break it up into is a couple parts for deriving the chiral anomaly. The first bit will be something called a resin integration, which is in the path integral. We have something which is going to be d of the conjugate fields, this one, Dirac field, and then it's going to be, let's get a new page, e to the let's do Euclidean signature. So E S psi. Oh no, let's just get rid of the dependence on that. We want to change this one instead into an integration over the Grassmann variables, which I will explain later, but let's just write them as this. And then it's going to be S. Let's write this here.
Jonathan, let me
Mhm.
stop you once again. I'm very sorry. When we talk about Euclidean signature, are we talking about the usual Euclidean signature where we turn from Lorentzian by taking t equals something imaginary? Is it something like this or?
Yeah, so the Wick rotation, right? So we start
Okay,
in
okay.
and then we Wick rotate the time component, and then the gamma matrices are going to pick I need to I'm not sure the formal technicalities if the gamma matrices are also meant to change under the Wick rotation, but the idea is then you have the transformation such that then all of the gamma matrices, at least in the signature, if you rotate to, um, if you Wick rotate, say, to the plus 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 signature, then the idea is all of these ones want to be I, and then we're going to have the anti-commutation relations equals to delta mu nu I, and so forth. Yeah, let me just move this up here. And then we also want the conjugate, the emission transpose to be this. Okay, so that's just the general idea of these in this plus plus signature. Okay, so that's the first part, the Beresin one. And then I'm going to talk about the, um, what do you call? Uh, oh, the Fujikawa heat kernel method. So the Fujikawa method, which is a very nice way to derive the anomaly non-perturbatively, and it has important connections. So let me just write this. So it's the non-perturbative method, and it's also got connection to some topological ideas, such as the Atiyah-Singer index theorem. Okay, so let's proceed with this. The first thing that's important is the Dirac operator is self-adjoint. Oops. So what this means in its formal context is we can define an inner product with our Dirac fields such that it's going to be the integration over the volume element times by this, um, like this one here. Okay, so in Euclidean signature, this is going to be a, what's it called? I forget let me just check the technical word for this. Yep, 1 second. Give me a sec. Oh, positive definite, that's right. So this one here is a positive definite inner product. Whereas say if we're working just with in the Minkowski spacetime, then it wouldn't be positive definite because you would have negative um, inner products as well. So we work in Euclidean, so then we can have these nice properties. And then we're able to apply just a general spectral theorem, which says that we can write, say, if we have the Hilbert space full of spinners, the Dirac spinners, we can write these as terms of a sum over the eigenspinners. So psi k is going to be an eigenspinner. So psi k eigenspinner with eigenval lambda k. So then you have I d slash psi k equals lambda k. And these coefficients that you put in front of the eigenspinners are what I was mentioning before. These are going to be the Grassmann variables. So A is going to be Grassmann. Okay. And then the other thing about the spectral theorem, so the important bits about the spectral theorem is that psi k forms a complete Hilbert basis. I think in particular it's meant to be dense in the Hilbert space. So it's going to be dense. And then the other thing is because these are self-adjoint, these are going to all be real. And this is going to be really important for the Fujikawa method later. But anyway, we can do the same thing for the conjugate ones. And instead, then we have the conjugate spinners, and then we have our other Grassmann variables. So these are the conjugate. Um, yep, the conjugate eigenspinners. Cool. Okay, so one other thing is that these may not necessarily, the eigenvalues may not necessarily be distinct, but because we can use our inner product to generally just impose that for all of them, even if the eigenvalues aren't distinct, that psi k, psi j is just going to be equal to the delta. So we're going to norm these ones to be all orthonormal. Oh, an important thing is if the eigenvalues were distinct, then because it's self-adjoint, this necessarily implies that they're going to be orthogonal anyway. That's just a simple result from linear algebra type or functional analysis type arguments, which I have in some notes that I've written up, but I'm not going to go through the details. So basically the idea, all of these are going to be orthonormal. Orthonormal with respect to the inner product that I mentioned earlier. Okay. So what we can then do is now we're able to use this to re-represent the half integral as the Beresin integration. So the first thing we want to do is take our action, which is going to be dv psi bar id slash psi. And then if we apply our the eigenspinners, then this will become J, K, B. Oh, sorry, I forgot to label these. These are meant to be K, and then this one's also K. Yep. So then this is going to be sum over BJ, AK, and then we pick out like a eigenvalue here. So these ones get like the lambdas. So then we have lambda k, and then the integration remains. So the eigen first one will be j, and then this one will be k. And then if this one is just the inner product, so this is just delta j, and then we're left with just s equals summa k, bk, ak, lambda k. Um, and then what we want to do is we want to represent the path integral. So if we just look at the measure, the original measure we're considering is something like this. Then one way you can interpret these psi's is say like as a, I'm just saying this very loosely, but the idea is this is say AK psi k. This is sort of like an infinite dimensional vector, A1, AK, dot, 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 dot. And like these bases are meant to be like countably infinite. So this kind of makes sense as procedure. So normally say like if you were to write say like DD X, what that really means is like in terms of an integration over d-dimensional spacetime, what we really mean by that is like a integration over just a variable vector, and that's meant to be formally dx1, dx2, dot, 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 dxn. So then we have the same idea where our measure, I'm just going to write it like this. The measure is meant to be the same thing as the product of k's, d, a, k, and so forth. Okay, so then when we apply that, then we can write our measure. So the measure is going to transform as psi bar, d psi is going to be psi k, dbk, dak, and so forth.
Stupid question.
So then the partition function just becomes z is going to be the product of these ones, dbk, dak, and then e to the minus, let me write this down, psych, sum over k, bk, ak, lambda k.
Excuse me,
So
Jonathan, can you hear me?
done, yeah, sorry.
I thought it's just a stupid question. So BKs are Grassmann and AK are Grassmann.
Yes.
So the ordering of the product somehow matters, but it's just up to a sign, right?
Yeah, so if you ever, let me just, I can do a brief recap on some of these important identities for the Grassmann one. So I'll just quickly do that.
Sure,
And
sure.
I
I'm
hope,
just wondering about the convention for the measure, like
yeah.
the ordering.
So the ordering is, I'm doing the, because we order the conjugate one first, and we have the B ones first as well.
Right.
Yeah.
But among the BKs, like B1, B2.
Yeah, so we're going to have it be just like this. dbk is going to be db1 all the way up to dbn. Well, it's not, it goes to countably infinite, but I hopefully get the idea. Or however much it goes up to. Yeah.
Sure, sure, sure. I'm just wondering. So this ordering is canonical in some sense because
Yeah. Yeah, it's important you pick the ordering
yeah,
because, as you said, because these are Grassmann variables. So these are Grassmann men implies that if you have B1, B2, they're going to anti-commute.
right. But this ordering comes from choosing to order like the eigenvalues of the Dirac operator in increasing order, say, and then you fix that ordering. I'm just wondering about this -1 sign possible ambiguity in like reordering the dbk factors, say. Is
Yeah.
it just a convention or is it actually possible?
That's a good question. And I would say I don't have a strong answer to that, but I would say if you're taking the correlation functions, normally you're going to divide by the vacuum values,
Oh yeah, for sure.
and then you're going to have, I'm just going to write dB, dA, and then you're going to insert your function, and it's going to be e to the minus s.
Right.
Then okay, so you can write this instead as like a fraction like this, dB dA e to the minus s. So if you pick like some opposite convention, then you'd also have to swap it in the vacuum one as well.
Yeah.
So then it would be, minus dA dB minus dA dB e to the minus s. But yes, there's potentially an ambiguity that could arise. I'm not going to cross this out. That could arise if you weren't dividing by the vacuum ones.
Yeah. Okay, thanks.
That's just my understanding of it so far.
Mhm.
Okay. I also, in my notes, I have some interesting properties about the Breslin integration, but I'm not going to delve into that because we don't actually need to really use that at the moment. But if we can come back to that later. Okay. It's one important note is that it's a formal device, and these aren't the same things as when I say measure, it's not really the Breslin integration isn't actually like measure theory integration type measure, but they're just a formal device in order to compute these half integrals of fermions. Okay. Yeah. So we've done that. So now that we've transformed it into this Breslin integral, now we can actually work on trying to compute the anomaly itself. So the idea is we want to see, so here we go. Oops, transformation under the axial one. Under the axial symmetry. So the idea is we want to see how our measures dA will transform under the symmetry psi goes to e to the I alpha gamma 5 psi. Okay. So let me just find where I've got this. Okay. So the idea is, say then we transform these ones. So there's going to be psi dash is going to, oh, this is psi dash. Psi dash is going to be, again, a summation of the eigenspinors, but instead now we transform the coefficients AK. And then on the other side, we have e to the I alpha gamma 5 psi k AK psi k. And then what we can do is we can multiply both sides by the conjugate ones. Let's put j's and integrate this over the volume element. Okay, so when we do that, we have integration dv psi j ak dash k equals dv psi k e to the I alpha psi phi. Oops, and I forgot also there's a k here, sum of a k psi k. And then one other thing to say is that because these are just coefficients, we can commute these around. So we just commute these, and then we're also left with the AKs. So these are going to give us a inner product, the delta JK. So then we're left with the AKs are going to be equal to the sum over the Ks dV psi j e to the I alpha gamma 5 psi k times by AK. Sorry, this is J. Cool. And we can do the same thing for the BKs, and then the BKs or the BJs are going to transform in a similar way, but actually let's write this as let's write this as a matrix. So we can think about this as a matrix, C, J, K, acting on K. And then the BJs, when you do the calculation, are going to transform similarly, but it's going to just have the indices swapped. So it's going to be like a transpose. Cool. Okay. And then, of course, the CJK is just going to be equal to this. Oh, there's the sum K's here. But I was just, the summation was implicit. But anyway. Yep. So then we have this one. We can then substitute this into the ward identities to derive the anomaly, but I will just continue with the Fujikawa method, and we can talk about the ward identities in a moment. But this is the idea of how these ones transform. So then we can substitute this back into the measure. So if we look at, say, now the measure, so we're going to look at the measure, and we have the measure dB, dA, and then after the U1 axial, the chiral symmetry transformation, these are then going to be dB dash, dA dash, and we're interested in how these transform. So one of the interesting things about Berezin integration, which I'm not going to delve into in this talk, is that in normal, let's have a comparison. So we're going to have Berezin down here, and then we're just going to have the normal, say like measure theory sense. If you have a transformation, say vector, d x is a vector, then let's write y instead. You can write this as the determinant of the Jacobian times by dx, where then you transform the vector x into y, and j is going to be dy dx with like these indices ij and so forth. Whereas with Berezin integration, it turns out it's going to be the opposite. So let's write it like this. What I mean by opposite is they transform as an inverse. So it's going to be determinant of this Jacobian-like element. And then they're going to be, let's put dash dA sort of thing. This comes out of the formal definition of Berezin integration and just how the anti-commuting natures of the Grassmann variables means that it's going to pop out an inverse rather than the standard determinant. Okay, so then we have our dB dash dA dash is then going to be equal to the dB dA, and then it's going to be determinant of the C matrix that I had before, which was the transformation. If I just scroll up, this one here, because we have A dash is equal to C A and B is equal to C transpose B. And importantly as well, these are independent of the Grassmann variables A and B, which is nice. And we're going to pick up two of them from each of the transformations. And also remember that the transpose of the determinant of a transpose is the same thing as the determinant. So then you pick up one of these. And then the idea is we just now need to compute this determinant term. So it is, sorry, the determinant of the Jacobian. So we're just going to call this a Berezin, analogous to like a Jacobian sort of thing. So just quick calculation gives us 1 over the determinant of C is going to be the exponential of minus the trace of the log of C. I'm sorry, that's plus, but that's inverse. And then we can bring the inverse down. And then so we get minus like this. And then importantly, the trace here is going to be over spinor indices because we're summing over the eigenspinor modes. Okay. So let me rewrite C. The matrix C is going to be JK. It's going to be dV psi j e to the I alpha gamma 5 psi k. And then the idea is, if you recall from like Taylor series, you can write 1 plus x is going to be x plus x squared plus dot 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 dot. So the idea is here, now we can formally expand the exponential, and so then we'll just have the delta function, the delta jk, plus the first order term, which will be alpha, so it is I alpha dv, and I already got dv, psi j gamma 5 psi k plus then alpha squared like terms. Okay, so the important detail for this calculation as well is then alpha is going to be small. So we need like small transformations as well. So then we can represent 1 over determinant of C is then going to be equal to e to the minus trace of this. I'm going to call this thing here x. So then we can say, actually, I'm going to cross this out. Then we can say that C is going to be I plus X plus the higher order corrections. So C equals I plus X plus the higher order corrections, where implicitly X is meant to be the one that I wrote over with the first order and alpha. Okay, so then this is going to be just the trace of X plus higher order corrections, which I'm going to suppress. Yeah. Okay. So then formally, we're going to have that our measure is going to transform as, let's put in the summation, k dbk dak is equal to, so k dbk dak, and then we have, if you recall, power 2, so the power 2 is then means it's going to be minus 2 trace of x, and then if I put in formally the other ones, sorry, write explicitly what is x, then we have e to the minus 2 trace of this one, so it's going to be the integral dv alpha, yeah, there's also, yeah, let me just write this out in a sec. Okay, let's write this. So then trace of x is going to be tracing over the variables, which was, let me write this, I dv alpha psi j gamma 5 psi k. And as this is a trace, then this becomes I dv alpha sum of k psi k gamma 5 psi k. So then if I put that in, then we have minus 2i, oops, sorry, it's blue, 2i dv alpha psi k gamma 5, this one. Okay, so then this one here is going to contribute to our anomaly term. So this will be the anomaly term in the ward identities. And for just next section, I'm going to talk about how you actually compute this one and simplify this thing further. Yeah, so in essence, let me also just copy this over. So then you can, to summarize, you have these the measures of the thing, of the Dirac spinors, is going to then transform as d psi thing, e to the, and then I'm going to copy paste this. Copy. Like this one. Okay. So then this is the anomaly term. Importantly, some interesting things which we'll see is that this will vanish in dimensions d equals odd, whereas it survives in even dimensions. And then as an exercise that's worthwhile to do would also be to consider to show that there's no anomaly term for the U1 vector symmetry. So it's basically the same arguments as I was just outlining before, but instead now you have to just show that these vanish to at least order alpha 1. So I believe that the alpha squared terms do survive for the vector symmetry transformation, but then for the axial one, it's going to remain. Cool. Okay, so the next bit is just about evaluating the bit inside the exponential, which will give the transformation. Okay, so this is where the Fujikawa method comes into it, is about evaluating these components. Okay, so let me write this. I'm just going to give this a name. The thing inside this bracket, sorry, inside the exponential, dv alpha sum of k psi k bar gamma 5. I'm going to call this thing an A field. So this is the common notation that's in the literature for these derivations and also just Fujikawa's original as well. So the idea is to evaluate this. So this is where so now that we've done this, this is where the connection to the Atisi index comes from when we try and evaluate this thing explicitly. So in particular, this is going to correspond to the index, or at least the integral is going to, over the space-time volume. Okay. So the key idea for evaluating this, I'm just going to drop the alpha term for the moment, but it's fairly straightforward how to re-include it. Actually, we're just going to evaluate A itself. So A is equal to psi k, like this, gamma 5, psi k. Then the idea is that this, we can multiply everything by 1. I'll also remember that the AKs were real. So then this method is going to work where we can insert, I'm just going to write it like this. We can insert 1 in the following form of writing, moving this over here and taking a limit of some mass scale going to infinity, e to the minus lambda k on m squared. And so this thing here is going to be known as the Fujikawa heat kernel. And then the important thing to realize is that e to the minus lambda k on m squared psi k is, because these are eigenspinors and these are the eigenvalues of the Dirac operator, these in particular going to be I d slash on m squared psi k. Okay. So then the next thing we want to do is we want to then bring the limit out, and so we can bring this out and leave this inside. Gamma 5 e to the minus id slash on m squared psi k. And then we can proceed with the computation for this. So the general idea is, and this is going to contribute, we perform a Fourier transform in order to get the Dirac operator in a very nice form where we can then expand this and do the following procedure. I'm going to just go through the calculations without, I don't have a particular nice physical interpretation of it. It's just sort of a computation that you just perform and it falls out. Okay. So you want to perform a Fourier transform, and when you do that correctly, I'm just going to skip a number of steps. You're going to want to Fourier transform each of these ones. So Fourier transform this one, Fourier transform this one, and then you want to use the idea that, let me write this down, that in particular, if you sum over the Fourier transforms of this one, the spinors, with the tilde, that's going to be the Fourier transform. Psi k with some just matrix inside X, a spinor matrix, which I might actually just write S to make it clearer. And then this one. This in particular is going to give you 2 pi d. And then because you're summing over these spinor matrices, it acts as a trace, and so then you trace over the thing inside. I don't quite understand completely the derivation for this calculation, and I can't find any references for how to do it, but this is the one that is generally quoted online, and it's the only way to get the calculation to work. But when you do it, then you will see that this A can be written as d to the d k 2 pi d trace over e to the minus I k dot x. You got your gamma 5 inside, you got your Dirac operator minus id slash on m squared e to the I k x. So the important thing about these this trace here, so I said that this is a trace over the spinor indices. And then as well, because we have our D's, D slash, we also implicitly have our gauge fields inside. So it's going to be over the spin indices and also the gauge group, the Lie algebra elements for that. So the gauge indices, that's what they're called. Indices. Okay. So using this, then we can proceed with evaluating this. So the next identity we need, which I'm not going to prove, but I'm just going to quote it, is this can be written as this inside can be written as minus d squared plus ig onto gamma 5 gamma mu f mu nu. And here I've used the commutator of the derivatives, the covariant derivatives are going to give minus ig f mu nu. So then this is, f mu nu is actually let's write this as differential form. F is then just going to be the curvature, of the gauge fields, the curvature on the bundles. Okay, so now that we have that, then the idea is we want to be evaluating this sort of expression, id slash on m squared e to the I kx. With our proof, I'm just going to write a few things. So I to the k dot x e to the d slash on m squared e to the I k dot x is then going to be equal to ik mu minus ig alpha mu. Oh, sorry, I wrote that wrong. Just with the derivative inside. And then if you were to do it again to have the higher order ones, so if you were to do d squared, which is just going to be the contraction like this. So that's the d squareds. Right, this d squared. This is then going to be minus k squared plus some terms that are going to be like of alpha, sorry, a mu in the gauge fields. So then the idea is that in these ones, when you then incorporate with the mass term, so the regularization, then you have minus k squared plus O. Oh, and then these are kind of like with the momentum terms as well, m squared. I don't completely understand why this step necessarily works, but then the idea is that a mu on m, this is going to go to 0 as m goes to infinity, whereas then the k on m terms, these are going to survive. Okay. So this general procedure allows you to expand the exponential and then recontract it. Sorry, bring it back together. So you take the limits in a formal sense, and then this gives you e to the minus ik dot x. Important, I've got to have the lim as well. Lim m to infinity, e to the minus ik dot x, e to the minus I d slash on m squared, e to the ik dot x is going to be equal to e to the, yeah, let's just keep the lim here as well, because this is actually important. M to infinity, e to the minus k squared on m squared. Okay, so then the gauge terms, the gauge fields are going to vanish in this limit. It's okay. So then we can put this into our expression, this one up here at the top. And wait a second. Sorry, I just realized I wrote this. Oh, no, this is fine. So there's the d slash. Sorry, I wrote this one wrong. This is meant to just be d squared up here. D squared on m squared. So these ones are going to turn like this. So then when we have our limit m to infinity e to the minus ik dot x, e to the minus id slash on m squared, e to the ik dot x, it's going to be lim m to infinity e to the minus ik dot x, e to the minus d squared on m squared plus, particularly this one's going to be minus, sorry, minus ig on 2 gamma mu gamma nu. Let me just check I wrote this one up here. Yep, so I got this one, just copying this one over. Then we have the curvature term, and then we have e to the ik dot x. So then when we evaluate this, we're then going to have limit m to infinity e to the minus k squared on m squared, and then we're left with this term here. Okay, and then we can put this into the trace, and then we have a equals sum of k psi bar k gamma 5. Then after with the regularization, this is then going to be equal to lim m to infinity trace gamma 5 e to the minus IG gamma mu nu F mu nu onto M. And then we're going to can take out the integral over 2 pi d e to the minus k squared on m squared. So then the next idea is then we can transform this measure in particular. So then it's going to be k on m times by md. Okay. So then this is just results in having to expand the exponential and can keep surviving terms. So in its essence, this is essentially the Fujikawa method is done. We just need to evaluate this trace. So our first few things just to say is in the dimensions, the the Gaussian integral is going to be d dx is then going to be, let me put this as like a vector notation. Hopefully this is clear what I mean by this, but please let me know if this is not clear. Is then going to be pi to the n on 2. So that's a nice result. So then the next thing, so this is going to basically simplify this integral up here. And then we just need to take the trace. So let's work in, for example, d equals 4 space-time dimensions. So this is, Euclidean space. And what we have is the following identities, that the trace of just gamma 5 is going to be the trace of gamma 5 with 2 of them, and this is 0. And then the trace of gamma 5, gamma mu, gamma nu, gamma rho, gamma sigma is going to be -4 times the totally anti-symmetric tensor, epsilon, mu, nu, rho, sigma. And then if we expand it, the surviving term that we're going to get some things that are going to go to 0 in the limit. Let me just write this like this. Okay, so ... This is going to equal, okay, one other thing, sorry, we're expanding the exponential. And then actually, let me just copy paste this over so it's clear. And I will get rid of this. And then in 4 dimensions, the one that's going to survive is going to be, give me a second. This is going to be minus I squared G squared M4. We also need M4 here. Let me not hide it. Let's put it here. M4. Then it's going to be 2M4 times by then the trace of epsilon mu nu rho sigma. To also make this more explicit. Sorry. Oh, I forgot there's a square in here. There's a typo somewhere. This is a square. And the other bits are right. Okay, that's fine. So then you have those ones, and then you have mu nu, F mu nu, F rho sigma. And then you have plus higher bits. So they're going to be something which is like, let me write this explicitly, IG gamma 3 on 48 m squared trace of like 3 of them, which I'm not going to write, and then plus higher things. Okay, so these ones is, the one in blue is 0 because of the trace, and then these ones are going to go to 0. because we're taking m to infinity. So the only idea is that the only ones that survive will be the second power of the expansion. So then we have A is going to be equal to lim m to infinity of dot 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 plus g squared on 2 trace epsilon mu nu rho sigma f mu nu f rho sigma plus bits that vanish. Oh, these ones are exactly 0, so let me write exactly 0 plus this. And then this is going to be order 1 on m squared. And then from the Fourier transform integral, we're going to get pi squared over 2 pi to the 4. So then when we evaluate this directly, we're going to get GA is going to be g squared on 32 pi squared trace of this one, f mu nu, f rho sigma. And then the idea is if we want to write this in as differential forms, we can do so, in which case we get, let me write this properly, this is going to be 8 pi squared trace of f wedge f. Okay, so this is a nice identity, which is going to be in 4 space-time dimensions. Without quoting, I'm just going to have this here for completeness. If we have d equals 2k space-time, we also get a similar expansion where we get a is going to be equal to g to the k, 2 to the 3k minus 1, pi k, 1 over k minus 1 factorial. And then we have the trace of the completely anti-symmetric one. The arguments are basically similar, where the only thing that survives is going to be the kth power of the exponential. Cool. Is that right? Yep. And then in principle, you can upgrade these to differential forms, but I haven't done that, but I'm sure that's not too difficult to do. Yeah. So now we can insert this back into the measure that we had before. So to summarize, the measure is going to transform as like this. So this is under the ABJ one. So this is the chiral symmetry, the chiral transformation. D psi is going to be d psi bar, d psi exponential of minus I g. Okay, so one other thing is just to recall, let me actually just go back up so I can make this clear. Sorry about this. Is when we had this, remember we have minus 2i, so then the 32 is going to become 16, and we pick up the extra factor of I. I also dropped the transformation parameter term alpha, but we can re-include this. In which case we're going to get minus RGs on 16 pi squared. And then we're going to get the integral of the volume, alpha. And then it's going to be the trace over f wedge f. And if we do that, it actually needs to be 4. And then so this is going to be the chiral anomaly. So this one here is the chiral anomaly in d equals 4 space-time dimensions. If you go through the Ward identity, so I don't have time to go through those technical details, but then the idea is that the variation of the action under so this is variation of the classical action under, well, this is any get under any continuous symmetry, continuous sim. You then, if you have let alpha be a space-time parameter, depend on space-time, you can then write the transformation as minus dv alpha x d mu. Oh, and this is also compact as well. So here we have our Nova current, and then using from the Ward identities, we have that inside the correlators. We have the anomalous Ward identity. So this is for the anomalous, is going to be equal to IG. Oh no, the I is going to vanish on 4 pi squared. And then it's going to be trace of f wedge f. Let me just check if I missed any minus sign. I think that should be fine. Yep, okay, that's good. Oh, and also, sorry, these are differential form. I'm writing this as differential form, so then we can write this instead as d of the Hodge star of the current. Let's make this a bit cleaner. Okay, so here's our Ward identity for the anomaly. So remember that if this was a true symmetry, so if this was a true quantum symmetry, then we should have that without any operator insertions, this should just be 0, which is not true. Hence, we have the anomaly, so the symmetry does not survive quantum mechanically, though the transformation is still allowed. I can also talk about the connection to T-Singer index theorem, but because of limited time, I will just skip that for now. But if there's questions about it, I can briefly mention that. I will, for next couple minutes, probably about 10 minutes, just mention how this connects to the idea of non-invertible symmetries. So this has already been quite long, but this is meant to be, say, the punchline of what we're doing with these anomalies, is that we can think about these anomalies, in particular these ABJ ones, as non-invertible symmetries. So the idea is you have these symmetry operators, but when they fuse, so I'm just going to write it as this. So the way to write it actually is with D's, but anyway, if you have D with some parameter, I'm just going to, without formally writing this, what this means, it's going to be if these two combine, then you're going to get, actually, let's just make this like alpha beta or something. Alpha beta, when you combine these two symmetry operators, in the sense of the continuous zero form ones, which I talked about a few weeks ago, this is then going to give you another one, but the coefficients are going to be topological field theory valued. I don't quite understand the technical details of that, but yeah, let me write this. You could just write it as like some topological field theory attached to this. Okay. Perhaps we can talk about that in the future weeks, how these technical details of attaching topological field theories work. But the general idea is you can construct these symmetry operators in very much the same way as we have before. So if I just, for the moment, ignore the correlator functions, we have that the anomalous Ward identity is the current is going to be 1 on 4 pi squared f wedge f. Oh, I should also mention that for the moment, we're just going to work in abelian gauge theory. So abelian gauge theory. So then we can write these Fs just as dA, where A is our one-form gauge field. I'm not familiar with how you construct this for non-abelian symmetries, but then for, sorry, a non-abelian gauge theories, but for at least for abelian, this works quite well. So you can write 1 on 4 pi squared F wedge F. This is going to be 1 on 4 pi squared dA wedge dA, which is then going to be, sorry, let me write this. This will then be, 1 second, dA wedge dA plus A wedge dDA. And then if we assume this will be 0, if we assume we have a trivial cohomology. So then we can apply like the Poincare lemma, which just says d squared of some form is going to be 0. Okay. So then using this, we can rewrite the anomalous nova current as 1 on 4 pi squared dA wedge dA, and then we can write this as d of wedge star j minus 1 on 4 pi squared A wedge dA is 0. So in some sense, we have conserved Nova current. But just one thing to be careful with is that these A's here are going to be gauge fields. So although we can try and construct a topological operator using this, we can't actually remove the anomaly. So we can't remove the anomaly, but we can at least attempt to write these things. So in the same way, we want to, since these are going to, we can apply things such as Stokes' theorem. We then want to try and construct these operators, symmetry operators on some codimension 1. Sorry, I should say that if let's call this thing d of star JA equals 0, where I'm calling this form JA star JA. So then we can attempt to construct, so let's say attempt, in the same way as we were doing before, as e to the I alpha, a charge operator. Sorry, I should say star JA is going to be a codim -1, which is 3dim, because we're dealing 4 dimensions. Yeah, sorry, this is 4D QED, because we have that. Then also sigma, our surface has to be codim 1 as well. So then we can attempt to construct it like this, with the general charge is going to be e to the I alpha sigma star j minus 1 on 4 pi squared A wedge dA, like this. So I'm just going to say leave it for here for the moment, but the idea is then you want to concede that these things can't be, there's some sort of issues with the topological field theory in particular. Let me actually pull up the paper because I think it'll be more worthwhile than me just reading this stuff out. But just give me a second. I'm just going to pull this up. But if there's any questions now, please let me know and I can explain that aspect of it. But I'm just going to pull up the paper that I'm referencing, which was one of the first ones for these non-invertible symmetries for QED. Okay, give me a second. We'll stop this. Oh. Stop. Let me just pull this up. Okay. So let me share screens again with this one. Share. Is this one it? Yes. Okay. So I can make this full screen as well. So this is the paper in which they construct the non-invertible symmetries in QED. But I see that these methods may generalize to other non-abelian gauge theories as well, but let's go next page. Oops, sorry, I don't know why it's doing this. Not sure how to keep it one page, but the idea is, as I was saying before, we can attempt to construct these operators, the symmetry operators in the same way as the zero form symmetries, but then they're mentioning about there's issues with the Chern-Simons theory, in which in order to get these things to be well defined, they need to instead write this bit in here instead, this bit here instead quantized using these new fields, where then A is going to be a background field, and then little a is going to be the gauge fields for the topological field theory. And then, as I was saying, to write these ones properly, you need to have certain ratios of the charges of the symmetry operators, and then these things are going to be well-defined operators. In particular, you can do it for the rational numbers of these rational ratios in something like this, where then these A's, these are going to be gauge fields, so these are going to be two-form background gauge fields. And then that allows you to define these topological symmetries, which they're going to be topological due to Stokes' theorem, as I was saying before with the zero form ones from a few weeks ago. And then the idea is, say, you can, in particular, when you fuse the two of them together in a sense of like fusing the surfaces, then they're going to merge together to give you another non-invertible operator, but this time with a topological field theory attached. I haven't gone through the formal details of this, so I can't give a better explanation at the moment, but I assume we can work through this in more detail in future weeks. But yeah, please let me know if there's any questions about what I was discussing today. Otherwise, we could, yeah, okay, I'm going to leave it at that for now.